All right, now that we know a little bit about vectors, let's see if we can look a little bit more in depth at them. So let's start out with like vector arithmetic. So how do we deal with arithmetic and vectors? Well, let's say generically speaking, we start out with two vectors. Let's call it the vector u, which is u1, u2, and the vector v, which would be v1, v2. How do we do arithmetic with these? Let's start out with this. What happens if I take a vector and I multiply it by a constant? Kind of like an example, if I had the vector u was the vector 2, 3, and I wanted to know what 2u would be equal to, or 2 times the vector 2, 3. Well, the good news is your intuition works well here. Now you're not actually distributing, because, well, this isn't a distributive property, but you are going to multiply every component by that constant. That's c times u1, comma c times u2. So over here, this would just be 4, 6. So what's actually happening when we multiply a vector by a constant? Let's draw our first vector. The first vector is the vector 2, 3. If I draw from standard position, remember that's from the origin. That says I'm going to start at the origin, go 2 in the x direction, 3 in the y. So that gets me to about right there. If I draw the vector 2u, that means it's going to go 4, 6. That gets me to about right there. Now I'm going to kind of draw a little bit to the side of it. So I know it's just kind of a quick sketch, but if this here is u and the whole thing here is 2u, you can kind of see that it ends up being, well, twice as long. And that's what's happening. This is called scalar multiplication. Because basically what you're doing is you're scaling the vector. So if you either multiply or divide a vector by a number, you're just changing its length. And you can prove it here pretty quick by just running this through our magnitude. We know from before the magnitude of a vector is the square root of the sum of the components squared. 1u2 squared. So what happens if I do the magnitude of a constant times that? Let's see if we can make it through some of this arithmetic. That's cu1 squared plus cu2 squared. Well, for each one of these, I could write this as c squared u1 squared, c squared u2 squared. Since on the inside, both of those have a c squared, on the inside I can factor that out. All right, well, now that they have things joined by multiplication, we can actually just take the square root of both of these. Now here's where this gets a little bit tricky, and it's something you're really going to have to watch out for. The square root of something squared is just not that thing. The answer to that is not just c. Because remember, we defined, when we first defined the square root, that it had to always have a positive answer. Since I don't know what c is, I got to make sure that it's positive by putting absolute values on it. So anytime you take the square root of something squared, or technically the even root of something raised to the same even power, you always get this absolute value. Now notice, what did we do to the original magnitude? All we did is end up multiplying it by this number, so we changed the length of it. So if you multiply by some constant, it is a scale, which means it doesn't change the angle, it only changes the length. So if our original vector was this length and we multiplied it by 2, we would double its length, but it would still point in the same direction. Now where this gets a little bit confusing, and I'm going to stick this right here in this picture. What if we would have done -1 times u? Well, that would be -2, -3. That would actually point down here. That would be -u. Now notice the length's the same because we multiplied by 1, but the direction's different. You know, kind of. Now what we mean by the direction's different, think about this vector here. Starting here at the beginning and ending up here, and we're going this way. If you multiply by a negative number, all it's going to do is make it point the opposite direction. But the overall direction is still somewhat the same. You'd say that it's parallel. Kind of like if there was a line that went all the way through here, you couldn't tell the difference if it pointed one way or the other way. What we mean by changing its direction is we mean some type of rotation of it. So if you do end up multiplying by a negative, it does just flip the direction exactly the opposite way. All right, so that's scalar multiplication. Let's take a look at some basic things like addition and subtraction. How would we actually add two vectors together, like u plus v? Well, that'd be u1, u2 plus v1, v2. Now the good news here is your intuition again works very, very well. All you're going to end up doing is adding these components together. So you're going to get u1 plus v1, comma, u2 plus v2. Now, what is this actually doing and kind of like in the real world? What does this mean when we add two vectors together? So if I gave you two vectors, again, let's make them easy, 2, 3, and 4, 1. And I ask you to do u plus v. Well, the arithmetic is very, very easy. That's 2, 3 plus 4, 1. Again, you don't need to write this out, but I'm going to go ahead so you can see it. 3 plus 1. So that gives me the vector 6, 4. Now, visually what's happening here is if we think about vectors as directions, remember it's kind of like directions how to get from a starting point to an ending point. Think about it as one set of directions, then another set of directions. So this says starting at the origin, go 2 steps in the x direction and 3 steps in the y direction. So that gets me to right there. Then it says from there, go 4 in the x direction and 1 in the y direction. So 4, 1, 2, 3, 4, 1 in the y direction gets me to about right there. So if you think about it, a set of directions and then another set of directions, well, if you look at the beginning, where did we start and where did we end? We started there and we ended there. Well, if this is the vector u, that was the vector v, then the red vector here represents u plus v. So it's kind of like where you started from if you went straight to the end. Now, subtraction, of course, since addition and subtraction are the same, works exactly the same way. So if we add u minus v, u1, u2, minus v1 and v2, of course that's just going to be u1 minus v1, comma, u2 minus v2. Now visually here, it is actually the exact same thing. Hold on, I'm going to grab another pen. If you think about subtracting, or one way to think about it, we're going to go in the u direction, then the opposite of v. So the opposite of v would be the same length, just pointing in exactly the opposite direction. So it'd be something like that. So let's see about where that would end up. So over here, if we did u minus v, 2, 3 minus 4, 1, 2 minus 4, 3 minus 1, that gets me a negative 2, 2. And if you look at the picture, it's not bad from the sketch I did. It's pretty close to where negative 2, 2 would be. So this here, this direction here would be that doesn't work. The opposite of v. So this side here again, if we go from start to finish, there to there, that would be u minus v. All right, so either adding or subtracting, you're thinking about going in one direction, then going in another direction. If it's minus, it just means you're going in the opposite of whatever that direction told you. All right, so you'd think now that we had scalar multiplication and addition and subtraction, that the next thing I would talk about would be multiplying vectors. Well, multiplying vectors is actually a pretty big topic all on its own, so we're not going to do that right now. So let's move on to just a few properties of vectors. Now, properties we mean is things you're allowed to do with them. Kind of like this. Our commutative property in arithmetic says that 2 plus 3 is the same thing as 3 plus 2. Well, good news for vectors, it's exactly the same. So you can kind of see the way that would work here. It wouldn't matter which one you wrote first, which one you wrote second, you would always get the same answer. Another one, let's say we have three vectors, u plus v plus w. U plus v plus w. It doesn't matter which ones you group together first. So you could say, I'm going to add u plus v, then add w, or you could add v and w, then add v. So this is our commutative property. This is called the associative property. Now, of course, this is of addition because that's what we're doing. So you're allowed to add them in any order that you want, and you can group them in any order that you want also when you're adding them. Let's see, a couple of the properties that you would recognize from regular old arithmetic. What happens if you take a vector and you add 0? Now, this is tricky because I can't add a number to a vector. It'd be kind of like saying I got the vector 2, 3 plus 7. That doesn't make any sense, right? This is one type of thing that's something completely different. So this thing here has to be the 0 vector. Now, a lot of textbooks don't actually define this, but the 0 vector is exactly what you'd think it'd be. It's just a vector full of zeros, whatever size it needs to be. So whatever dimension u is, it's 2 dimension, 3 dimension, whatever, the 0 vector can be the same size. Now, of course, if you add nothing to something, you get the exact same thing back. Kind of like if for scalar multiplication, if you multiply by a 1, you also get the exact same thing. Now, just so we have some properties in the same place, we had this one on the board a minute ago. If you find the magnitude of a scalar times a vector, it's really just the absolute value times the magnitude of the vector. All right, just a few properties just so we know that they go by basically the same rules as our regular number system does. All right, let's take a look at something called unit vectors. Now, we've already seen the unit circle back in trig, and we kind of talked about it in the last class. The unit circle was a circle that had a radius of 1, while a unit vector has a magnitude of 1. Now, the nice thing about having a magnitude of 1 is, we haven't talked about it yet, but if you multiply by something that has a magnitude of 1, it really doesn't change the overall size of anything. Kind of like we just multiply anything by 1, you get the same thing back. Basically, the only thing it would be contributing would be its direction. So how in the world could we make a vector a unit vector? Well, we said if we take a vector and we multiply it by a number, we change its length. So imagine this, if I took some vector u and I multiplied it or divided it, what do I think about it, by its magnitude, that would make it have a length of 1, right? I mean, if you take a vector that has a length of 7 and you divide it by 7, it has a length of 1, scales it down. And we need another notation here. Again, not always in your book. Anytime you see this little hat, little caret thing on top, that means the unit vector. So if you see a little hat on something, you're being told that that has a length of 1. So to make a vector a unit vector, all you got to do is divide by its magnitude. So, all right, so let's say I said make the vector u 3 for a unit vector. How could we do that? Well, the unit vector u, that just means the unit vector that points in the exact same direction as u. All we'd have to do is u divided by the magnitude of u. So let's go over and do some little quick side work. The magnitude of u would be the square root of 3 squared plus 4 squared. 9 plus 16, 5. So to come up with the vector that's in the same direction, we would take our vector 3, 4 and multiply it by 1/5 or divide by 5, either way you want to think about it, which would give us the vector 3/5, 4/5. Okay, so now we have a vector that points in the exact same direction as u but has a length of 1. Which means if I ever wanted to do something like this, here I have a vector that has a length of 5. What if I wanted another vector that pointed in the exact same direction but had a length of 17? All you have to do is, well, make it have a length of 1, then whatever you multiply it by, that'll be its magnitude. So if I wanted this thing to have point in the same direction to u but have a magnitude of 17. I'd make it a unit vector, then multiply by 17. So very, very straightforward. All right, now that we know what unit vectors are, let's take a look at what we call standard unit vectors. No matter what coordinate system you're in, there's directions in which things are measured. In our rectangular coordinate system, we measure things in the x and y direction, and of course, the z direction when we add a third dimension to it. So standard unit vectors are unit vectors, length of 1, that point in the directions that your coordinate system is measured in. So if I were to come over here and say, okay, that vector there has a length of 1, that would be the vector 1, 0, right? Only points in the x direction. Well, in this coordinate system, we actually give this a specific letter, and we call it I. And of course, I got the hat on it because it's a unit vector. So the unit vector, or standard unit vector that points in the x direction is I. I go up here, that would be the vector 0, 1. That's the standard unit vector that points in the y direction. That would be j. Of course, the way that I have this particularly drawn here, k would be coming straight out of the board at you, and you can kind of guess if the x is I, the y is j, then of course the three-dimensional unit vector would be k. So another way to think about this in 3 dimensions, this would be 1, 0, and of course that doesn't have any z component. That would be 0, 1, 0, and k would be 0, 0, 1. Now, you can always scale a vector up to any dimension that you want, right? Any 2-dimensional vector, kind of like our vector 3, 4, I can write that as a 20-dimensional vector if I want. It would be the vector, oh my God. It'd be the vector 3, 4, 0, 0, 0, 0, 0. So, y'all see what I mean? You can always add zeros to make a vector any dimension that you want. So most of the time we consider I just in 2 dimensions, but if we were to move it up to 3 dimensions, then of course that extra dimension is 0, because we're not moving any in that direction. Now, by using our standard unit vectors, we can actually come up with a second component form, a second way to represent the component form of a vector. And here's what it looks like. Something like this, 2i plus 3j. Now, for those of you that have already taken engineering classes, you've probably seen this notation. Because in the grand scheme of things, engineering type applied classes tend to prefer what we call the IJK notation, hence the IJK, where physics and, say, math performs the bracket notation, the one that we've been using up to this point. Now, I'm just going to show you that this really represents the exact same thing as the bracket notation. Watch. If I were to take and put in what I and j are here, I is 1, 0, plus j is 0, 1. We multiply a vector by a constant just by multiplying every component. So that's 2, 0, plus 0, 3. And we add vectors together by adding the components. So 2 plus 0 is 2, 0 plus 3 is 3. So you can see that this form and this form are exactly the same, just written slightly differently. You're going to have one that you prefer, but make sure that you understand both. The reason I think that a lot of engineering courses prefer this one, see if I had 2 vectors here, 2i plus 3j, and let's say v was 5i minus 10j, and I ask you to do u plus v, that's 2i plus 3j plus 5i minus 10j. Now, without ever having to understand what vectors are and which way things move, you can see all you got to do is combine like terms, right? If you combine the I stuff together, you got 2 and 5, which gives me 7i. And we combine the j's, we get negative 7j. So you can see that arithmetic with them may be a little bit more intuitive in the IJK notation, but most of the semester I'm generally going to stick to the bracket notation. But you do need to be aware of both notations when you're working through the homework.